good morning once again, and thank you very much for joining the Center for Data Archiving, Management, Analysis, and Advocacy, CDAMA for short, for our first monthly webinar series for the 2024-2025 academic year. This is going to be a regular event on our calendar, and anytime it's time for such an event, we'll send you the invitation link for you to join. Today's session will be looking at research data management. Before we launch onto our activity, let me introduce our panelists, and then we continue with our activity. So myself, I'm William Godfred Cantor. I'm with the Department of Data Science and also the coordinator for the Center for Data Archiving, Management, Analysis, and Advocacy. And now we have Dr. Raymond Kofinti, a data curation expert. Dr. Kofinti will take us through research data management, planning for data management, data collection and documentation, data storage, and security. So, Dr. Kofinti, please, you have the floor.
Thank you, Dr. Cantor, for setting the pace and the tone. As Dr. Cantor mentioned, I'm Raymond E. Kofinti. I'm a lecturer in the Department of Data Science and Economic Policy at the School of Economics. I am delighted making a contribution to our maiden Center for Data Archiving, Management, Analysis, and Advocacy workshop. It's not showing. Okay. So I will be making my contribution largely on research, data management, and my presentation will cut across 4 main domains. So I will start by introducing research data management, talk about data management planning, DMPs, issues involving data collection and documentation. Then I'll go for a closure on data storage and security concerns. I will start my main issues by drawing our attention to Figure 1. Figure 1 shows research data life cycle, which spans 5 main phases. The first 3 phases has to do with planning, creation, or the data generation process, that is phase 2. The third phase has to do with data dissemination. Unfortunately, 80% of research undertakings reaches their closure at the dissemination phase. And this leads to utility deficit in terms of scientific data management and stewardship. Research data life cycle persists to data preservation and data reusability for the research community to have optimal benefits from any research undertaking. Closely linked to Figure 1 is my operational definition for research data management, which is a catalog of activities or processes involved in organizing, storing, preserving, and sharing of data collected during and beyond a research project. The intent of these catalog of activities or web of activities is to ensure that the research data is accessible, reliable, and usable throughout the research undertaking and beyond. Reflecting on this component of research data management from organization up to data sharing shows that research data management is inherent in most research undertakings. The only challenge is that researchers do not formalize the process. So what are the constituents of research data management? Well, the component of research data management can be varied or numerous, depending on the discipline. But however, there are some overlapping domains. Irrespective of the discipline, there will surely be data generation, creation, or collection process of a research undertaking. Then there is a need to incorporate quality controls. This is to safeguard data integrity and minimize the incidents and impacts of errors. Data documentation as another key component is important for activating a seamless workflow and also for accurate interpretations of the outcome of the research. Anonymizing data is also important to filter out sensitive information as far as data is concerned. We can move on to data preservation, which has to deal with filtering relevant information that can be archived for reusability. Other components include data sharing, oversight responsibility, and organizing the entire research process. So all these components, or each of them has their own respective utilities. This leads me to the question, why do we have to bother about research data management? On one hand, it improves research data to support the fair guiding principles of scientific data management and stewardship. And figure 3 encapsulates the 4 items under the FAIR principles, making our data findable, accessible, interoperable, and reusable. These will allow researchers not to have credit only for their papers or publication, but also for the underpinning data. Other benefits also include immunity against accusations and misconduct, given that the research data management, or RDM, lays bare the protocols that are followed as far as the research process is concerned. Other benefits has to do with promotion of open access, replication of research, and open scholarship ideals. At this juncture, I would like to add that the foundation of any successful research data management lies in a well-structured data management plan, what is known as DMP. And it aligns with the saying that goes with, if you fail to plan, then you are really planning to fail. Research data or data management plan is very important to the researcher, and it is an immersive approach because it involves forward-looking and anticipation beyond data creation and generation. DMP is also a living document, meaning it is by no means static, it is not cast in a stone, and it has to be dynamically updated as the entire research process unfolds. Data management plan must cover the strategies, the tools, and people involved in the research process. These strategies must align with best practices within a given discipline. The tools deal with the machines, the software applications, and algorithms that are within a particular discipline. In fact, how strategies and tools are interfaced with the people in the research, that is what gives credibility to a successful research data management plan. Not surprisingly, data management plan is becoming increasingly mandatory within the funding space. A typical example has to do with the National Science Foundation as far back as 2011. It's a requirement, and this is basically a two-pager document. The same has to do with the National Institute of Health. Their 2023 policy documents that all grant applications and those that are to be renewed must include a robust and detailed plan on data management and planning. It is not only limited to these two funding agencies. A little search will show you that other active entities are also involved, such as the Social Sciences and Humanities Research Council of Canada, the Australian Research Council, ARC, Dutch Research Council. All of them are into mandatory data management plan to process a grant application. Given this, what then are the elements of a data management plan? The elements are numerous and valid, but the key ones are reflected in figure 5. A good data management plan should be crystal clear about the types of data involved in the research process, contextual details from the perspective of metadata is relevant, issues on storage, backup, and security to avoid data corruption and complete loss of data must be incorporated. Provisions should also be made for protection and privacy of data, policies for data reusability, accessibility, sharing, and archiving should be included. A major component has to do with roles, plan, and oversight. And it goes with the saying that everybody is on the project, but nobody is really responsible. So roles must be assigned to engender responsibility. I have to add that in each of these elements, you must plug in the STP guiding post. I know you have forgotten about the STP guiding post, but the guiding post has to do with strategies, tools, and people. And this is very important when it comes to data management planning. And that is basically what gives that credibility to a successful data management plan. So if you pick types of data, what are the strategies, the tools, and people involved, and how these will be interfaced is critical. Now I'm narrowing down to two components having to do with data collection and documentation and data storage and security. How you go about this process. involving data collection and documentation, especially within your DMP, data management plan. You have to come out clearly with the data types, the format, and the size that the project will generate or the project will capitalize on. These really portray the understanding of the data you will be working with, and it has implications for data security, data storage, and accessibility. So data types, I cannot be exhaustive over here, but it's varied. Whatever constitutes the factual facts, the facts underpinning your study, the facts and figures that underpin your study will become a data. And data is increasingly moving away from the conventional terrain. So there are a lot of nuances within this space. So I am not trying to be exhaustive over here, but as much as possible within your data management plan, what constitutes your data must come out clearly. And formats are very important because of interoperability and also seamless integration to other databases. You have to also come out clearly on the amount and size of data that the project will generate, and whether the data generation process will be constant across the project or it will be cumulative. Some projects may span 36 months all the way to 3 to 5 years. So it is very important you are clear about the amount of data that will be generated. The data collection methods, a decision has to be made on this, and at the collection stage, a lot of considerations must come handy. And I've listed some applications in this table, which by all means are not exhaustive, but my main take home has to do with compatibility issues and interoperability issues. You really have to have that consideration, whether the application, such as the Kobo toolbox, the red cap that you use for data collection, or any tool within your discipline, the operating system that is compatible, as well as whether it is open source, which is very important for replication of your processes. So the data management and inventory tools should also come out clearly. And this is also discipline specific. But in research projects that numerous data will be generated, as well as over time, information about data inventory tools that can be used to track the data is paramount. You must also leverage on metadata standards. And this has to do with metadata schemas, issues with labeling, tagging, and the coding system that will be cataloged in a structured format. And technical standards should also be specified. And these technical standards should have a convention dealing with repeatable tasks to enhance uniformity and comparability across the research period. And standard protocols involving data format, data dictionaries, codebook, issues on identifiers, unique identifiers are also to be flagged. These, as I mentioned, It's an immersive and forward-looking approach as far as the data integration processes are concerned. Then moving swiftly to data storage and security. Data safety should be on the table, and this has to do with the welfare of the research participant, as well as the integrity of your research data. Issues on data security from the perspective of confidentiality and how sensitive information is managed, and issues on operational and functional software applications to prevent data loss and data corruption, as well as appropriate warehouse for hardware, including the computers, the servers, and data storage should be incorporated in a successful DMP, data management plan. On storage, during the active phase of the research project, these can be institutional cloud and local network storage. These has to do with storages such as the OneDrive, the Google Drive, Dropbox, etc. You can consider this within an active phase of the project, and you should incorporate automatic backups, and as much as possible have the resulting data files can be deposited in general purpose data repositories such as the Dataverse, the Figshare, Zenodo, Data Hub, and Dance. All these are general purpose data repositories that are machine readable. I'm going to go for a closure of this presentation by offering 5 best practices of data storage and security. The first one has to do with the type of data you are working with and the sensitivity of the data should dictate where and how the data needs to be stored. It's very important. It should not be business as usual. Data filtering is also very essential so that the relevant component of the data that will be preserved is known, and the components that are to be shared are scrutinized based on ethical, legal, and technical considerations. Oversight, data management, preservation, and sharing is also very important. There should be assignment of role. All of us cannot be responsible. There should be assignment as far as accessing data, the data storage, data reusability. Roles must be assigned and individuals becoming responsible. There is that need for a companion metadata for archival information packages, and it must have adherence to standards such as data formats, dictionaries, code books, definitions, unique identifiers. This is very important because some research can span for close to a decade and even beyond a decade. And the baseline must have all this important information. Finally, in data storage and security issues, formats are utilized. This is important because there are concerns or opportunity costs of data loss in moving from one platform to another that is not so interoperable or compatible. So these decisions must be made a priori within the data management plan to ensure that the research data management process is transparent for us to reap the reward of scientific data management and stewardship. So these are some of the references underlining this brief presentation. And I want to thank everyone for your time.
Thank you very
and
much.
Dr. Kanta, over to you.
Thank you very much, Dr. Kofinti.